Hello and welcome to Begin Play, an Unreal Engine onboarding for developers. My name is Sebastian Hernandez, and I'm an evangelist for Unreal Engine. In this overview, we'll go over Unreal's audio system. Unreal Audio is a full-featured and incredibly flexible set of tools, empowering your team to design, mix, and process your project's soundtrack over a variety of formats and hardware schemes. You can target anything from regular stereo speakers to third-party surround solutions, and even drive controller haptics and gameplay systems. Let's begin by reviewing the full workflow. Unreal can play sound from a variety of sources. Some exist as in-engine assets, some are captured in real time from external sources, some are procedurally generated, and some may even be looped back from the sound system itself. Unreal treats all sound sources interchangeably, and you can play and control any of them using the same set of tools. You can create sound source assets in a variety of ways, from importing sampled WAV files authored in external applications to synthesizing and recording audio within the engine. Sound waves are the most common type of source asset, and they represent sampled sound data. Metasounds, which are authored in an integrated design environment, use visual scripting workflows similar to materials or blueprints. Metasounds provide more advanced functionality, including synthesized and interactive audio. Once you tell Unreal to play a sound source, it becomes active. Active sources are rendered and sent through a first stage of processing that can include 3D spatialization, attenuation, and other effects. After this, sound sources go through the mixing pipeline. Here you can group active sound sources and apply effects and modulations over part of the signal. The results are processed in a hierarchy and can either output to speakers, feed back into the audio pipeline, or provide signal data to other system endpoints. This data can also be analyzed by offline and real-time processors and read into other systems to provide visual effects and gameplay that reacts to the game audio. Throughout the process, Unreal provides a comprehensive set of profiling and diagnostics tools to help you control what's happening behind the scenes. Let's go back and talk about sound asset importing and creation. Most effects, dialogue, and music data will be authored in external tools and imported as sample sound files. Unreal supports many standard file formats, including WAV, OGG-Vorbis, FLAC, and AIFF, as well as a variety of bit and sample rates. To match Unreal's internal format, use uncompressed 16-bit files with a sample rate of 48 kHz. Unreal supports mono, stereo, and multi-channel sound files. There's also several ways of creating, capturing, and exporting sound wave data from within the engine. The Metasound editor includes ways of synthesizing and recording sounds. All you need to do is add a wave writer node to your Metasound graph, and you'll sample it into a wave file every time you play it from the editor. If you're building sequencer animations, you can use the Take Recorder to capture your microphone input. This will not only record sound wave data, but also synchronize it to the resulting sequence asset. This audio was recorded from within the engine. This audio was recorded from within the engine. You can also save a sound submixes output to a file. This enables you to record live gameplay audio while benefiting from all the features of the mixing pipeline. Importing will result in a sound wave asset. This represents sampled waveform data that can be played back by Unreal. Soundwave supports several types of data compression schemes, including PCM, ADPCM, and Bing Audio, as well as many platform-specific codecs. You can configure these for each individual asset to control its quality. Starting in Unreal 5.1, sound waves can be modified within the engine with a specialized editor. This enables you to do trims, fades, and other adjustments without relying on separate applications and re-importing. There's also the dialogue system, which extends sound wave functionality to organize context-sensitive conversation data. Dialogue voices define your characters and include properties to determine their gender and plurality. Dialogue waves rely on voices to select the right lines depending on the speaker and the audience. They also have built-in captioning support that ties into Unreal's text localization system. You can set the speaker and audience context from Blueprint before playback to get different results. Though it's not a full conversation system, dialogue waves simplify the process of building and localizing interactive conversations. Speaking of localization, it's easy to override wave assets for different cultures through the Localized Assets feature in the content browser. As long as you're using the same asset names and folder structure, Unreal will automatically map these sounds for the set culture. Be sure to check the documentation for more details. New to UE5, the Metasound editor is a fully integrated sound design environment. It uses visual scripting to quickly build sound playback and processing pipelines. Metasound supports logic-based sound mixing and digital signal processing, and it can be used to author smart interactive audio that can be driven from gameplay or other Unreal systems. Basically, Metasounds are two audio workflows when materials are to rendering. It's important to understand that a Metasound is not a blueprint, but rather a DAG, or Directed Acyclic Graph. This means that there's some limitations to how you can connect the nodes, the most important of which is that you can't loop back the data flow. There's some ways around this, and we'll discuss them in a moment. You can create a Metasound source asset from the content browser. If you're working in a project migrated from UE4, you may need to enable the Metasound plugin first. You may also notice that there's another type of asset called a Metasound patch. These are similar to function libraries in materials and blueprints and let you define a fragment of a Metasound graph that can be maintained independently and can be reused across many Metasound sources. Metasounds provide several means of generating audio. They can coordinate playback of one or more sound wave assets through wave player nodes, which can then be blended and processed throughout the graph. You can also synthesize sound with sine, square, triangle, and saw oscillators, as well as noise generators. These can be mixed into an output audio signal or used to modulate other data. They are perfect for retro-style sound effects and chiptune music, and they have memory and CPU performance advantages over sound waves. Metasounds also provide control and modulation functionality. You can store data in local variables and reuse it throughout the graph. This can help reduce a lot of the clutter in more complex Metasounds. Many common Unreal variable types are supported, as well as Metasound-specific types such as time and sampled audio signals. You can define array-type containers for any of these. Triggers are a deceptively powerful variable type. You can use them to define custom flow control events that can be fired from elsewhere in your Metasound graph, such as a finished playback event on a wave player. To place a trigger event, just drag the variable into the graph. To fire it, shift-drag it. Triggers can help you get around the no looping restriction in Metasounds. When you fire a trigger event, it will signal all the trigger flow connections on its next sample evaluation. They are perfect for establishing complex playback loops and sequences. There's also other flow control and data selection nodes that can help you delay and repeat playback, walk through arrays in a sequential or random order, and notify you when a sound wave or envelope has completed. Metasound has specialized nodes to control and modulate audio signals. Crossfades can smoothly transition between two inputs. Envelopes can provide time-based modulation. Low-frequency oscillators, or LFOs, can generate periodic signals that are useful for a variety of modulation effects. Most digital signal processing in Metasounds can be done through simple math operations, such as adding audio values into a single output or multiplying them by a float to amplify or attenuate them. Metasound provides a lot of convenience nodes to handle more complex math for you, such as filtering techniques and multi-channel mixing. For example, you can use a low-pass filter to simulate muffling, or high-pass for a radio chatter effect. Advanced effects such as frequency band splitting are also supported. Sound engineers with coding experience can build more functionality with the Metasound patch assets we mentioned earlier. They can also implement their own effect nodes in C++. By default, Metasound sources output a mono signal. You can switch to stereo and multi-channel output from the Asset Properties panel. You can add custom outputs in any supported variable format. These are useful for calculating and returning extra data on Metasound patches. The trigger type is especially powerful as an output. They can turn a Metasound patch into a self-contained playback logic box. Inputs help you control Metasounds through external data. Any variable type can be defined as an input and set from Blueprint or C++ through a parameter interface. By passing input data into a Metasound, you can create interactive and reactive game audio. Triggers are also supported as an input type, and they let you control complex state-based sound effects from gameplay, like charge-up weapons or a door with arbitrary open and closing times. You can execute trigger inputs while playing the sound from the editor by clicking on the Simulate button. There's no need to jump into Pi to check how your logic would play out. Float and time inputs can have widgets applied to them. Widgets change the node representation on the graph to either a slider or a knob. You can tweak their values while you play the sound, and they are great help when fine-tuning them. Interfaces are a way of communicating with other Unreal systems through a set of predefined inputs and outputs. Metasound defines interfaces to read attenuation and spatialization data into the graph. By default, Metasounds will continue playing until explicitly told to stop. The one-shot interface enables you to automatically finish sound playback from the Metasound itself, while notifying any Blueprint event listeners. All Metasound interfaces are optional, so feel free to add only those you need. You should expect more interfaces to be added to Metasounds as Unreal Engine development continues. Finally, we have Metasound presets. These are similar to material instances. You parameterize parts of your graph with inputs and then create variants that share the same overall graph structure but with different input data. By parameterizing frequencies, durations, or source wave assets, you can create entire families of sound sources that can be easily maintained. To create a preset, just right-click on a Metasound source on the content browser and select the option from the menu. The graph will be represented as a single node, similar to a patch, with connecting input and output pins and editable values for the inputs. Now let's discuss the remaining sound source types. Keep in mind that all sound sources can be used interchangeably and have the same core properties. If you're a coder, you can generate procedural sound with C++ by implementing the iSoundGenerator interface. This is a low-level class used throughout the audio system, and many sound sources use it, including Metasounds. Unreal also supports external streamed audio, including voice over IP. The media framework can handle sound and video streaming sources. Epic Online Services can be used as a voice chat provider, and the engine comes with a plugin for easy integration. Finally, the audio capture component can be added to actors to read live microphone data. You can route it through the mixing system to play it or modulate other sound sources. There's many different ways to play a sound source. We'll cover 3 broad categories of sound playback and control: sources placeable in a level, asset workflows with integrated sound support, and explicit playback through Blueprint or C++ code. The ambient sound actor is the easiest way to play sound in your level. Just drag and drop one of these and point it to the right source asset. You can easily control these actors' properties from Sequencer and your level blueprint. Audio volumes and the new audio gameplay volumes introduced in UE 5.1 allow you to control audio mixing and filtering on specific zones on your level. For example, they can drive a transition from an outdoors environment into a cavern with lots of echo. Audio gameplay volumes are modular and let you specify the features you want to affect by adding components to the actor from the Details panel. Each audio gameplay component has its own properties and functionality. The audio component provides finer control. You can add these to your custom actor classes either in Blueprint or C++ and treat them as a sound playback hub that can be moved and controlled like any other component. They are great for playing more complex Metasounds and changing their inputs in real time through their parameter interface. Sequencer supports sound playback through audio tracks. They are great for controlling sound and music playback during cutscenes and other complex scripted sequences. You can also animate Metasound inputs and fire triggers from the timeline by expanding the subtracks. Speaking of animation, it's easy to add sound effects to your skeletal mesh animation sequences through notifies. This is useful to play sounds synchronized to specific actions, such as footsteps and attack swooshes. You can even get more control by building custom animation notify classes. Niagara can also play sound through its built-in audio modules. This is a very convenient way of synchronizing sound and visual effects, such as explosions and crashes, and can save your audio and VFX teams a lot of time. Audio modules support input parameters, so it's possible to drive complex metasounds directly from a particle simulation. The easiest way of triggering sound from code is through the Play Sound Blueprint nodes. There are several variants from simple fire and forget to ones that support spatialization and persistent control. Like with all things Blueprint, there's also matching C++ functionality available. Quartz is an advanced timing system introduced in UE5. It can help solve sound synchronization and drift issues or react to music timing from gameplay and create rhythm games. Most sound and drift issues come from the fact that audio rendering and gameplay normally happen in different threads, and there's a small lag every time these threads have to communicate. Quartz deals with this through configurable clocks. You can set these clocks to match a time signature and then cue sound playback at the next available timing boundary, for example, at the next beat in the music. This makes it possible to create interactive music or sound systems while keeping sample-accurate synchronization throughout your game. Quartz clocks also let you subscribe to timing boundaries and trigger events on your game thread. This gives you the basis for creating rhythm-based gameplay that stays synchronized to the music. It's also worth discussing one important feature of Unreal's audio system. Stream caching organizes sound wave data on your project to optimize memory usage. It ensures that only data blocks that are on demand for playback are loaded into memory, and it's the audio analog of texture streaming. The caveat of stream caching is that if a sound wave block is not currently loaded, playback won't start until Unreal streams in the relevant data, which can result in a noticeable delay. You can prevent this by explicitly priming sound assets from code. You can also set a sound wave's default priming behavior from its properties. We recommend priming on load for timing critical sounds such as UI, footsteps, and gunshots. All active sounds are rendered by the audio system and then go through a digital signal processing pipeline. You should be careful about the complexity of any effects applied at this stage, as well as the number of active sound sources those effects are applied to, because you can bottleneck the sound system if you exceed the available resources. Sound concurrency settings are your first line of defense against this. They can define a budget for the number of sound sources in a group that can play at the same time. If this budget is exceeded, some sounds will be dropped from the mix. You can create these settings from the content browser and assign them from a sound sources details panel. This way you can easily reuse and control settings presets across many sound assets. The same applies to other setting presets we'll introduce in this section. All sound sources support individual volume and pitch settings, and many playback systems provide built-in randomization mechanisms to provide a cheap and simple means of adding variety to your game sounds. Unreal uses volume and attenuation data to determine if a sound's result loudness is low enough that it won't be detected by the listener. Normally, sounds deemed silent are called from the rest of the pipeline. One-shot sources are skipped, and looping sources are checked at regular intervals. You can override this behavior with the Play When Silent virtualization mode. You can specify a list of source effects that will apply over an active source. You do this by creating a source effect chain asset and then populate it with source effect presets. Source effects are a means of applying digital signal processing, or DSP, over a sound source to modify the volume, pitch, and repeat of the signal. Common effects include equalization, reverb, and filtering. It is worth noting that source effects do not support surround. Because effect chains and presets are content assets, it's easy to reuse them across many sound sources. Attenuation settings define the way your sound sources are faded and processed based on their location relative to the listener. Unreal supports many attenuation techniques, which include distance decay and muffling functions, attenuation shapes, which are useful for simulating sound coming from objects such as pipes and megaphones, and the ability to attenuate sounds based on phasing angle and obstructions between the source and the listener. Spatialization alters the sound signal for each of your speakers to trick your ear into thinking a sound comes from a specific direction. You can switch the spatialization technique from the attenuation settings. Binaural can provide better results on headphones by adding a small delay based on the direction of the sound. Because source processing tends to be very specialized and sometimes hardware-specific, Unreal supports third-party extensions through the source data interface. So if you're looking for vendor-specific support, you should check if they provide a matching plugin you can add to your project. In general, it's best to think about your concurrency and attenuation settings early in your project and assign them to sound sources as you create them, rather than to do a large push later on. Even so, if you ever need to edit asset properties en masse, remember you can do it quickly with the Property Matrix tool. Once individual source processing is done, active sounds are sent to mixing, where their signals are combined and then further processed as a group. This is similar to the post-processing stage in the rendering workflow. The core of the mixing process is the sound submix asset. A submix defines a combined signal collected from one or more active sound sources. A submix has its own DSP pipeline that applies over the combined signal. Submixes scale much better than source effect chains, and you can be more ambitious in the level of signal processing that you can apply here. Sound submixes are organized into a submix graph. This graph defines the order and dependencies of submix processing. You can have child submixes act as sources for higher-level submixes. You can also define a master submix from your project settings. This will act as the rightmost submix on your graph, and any submixes that don't explicitly define an output, as well as any sound sources that don't define a submix send, will automatically feed it. You can also create audio buses. An audio bus can also receive and mix sound source data, but unlike a submix, this data is not automatically fed into the output signal. Unreal includes specialized bus types. Source buses are considered sound sources and can be assigned to ambient sound actors and similar. They can be useful for remote interactive sound playback, such as radio systems. You can reference audio buses and other stages on the workflow, including modulation and Metasounds. This way, you can feed parts of the audio signal back into the pipeline for additional mixing, processing, and sidechaining. Just like textures can be used across multiple materials, a sound source's playback signal can be sent to more than one submix or bus. There are several ways you can control this. At the asset level, each sound source has properties to send to submixes and buses. You have a lot of control here, including the sound level to send to the mix and whether to send the signal before or after source effects are applied. Your attenuation settings can also specify a list of sends that apply to all sources that use their properties. This is a great way to apply blanket submix settings for a large number of sound assets. Sound classes can provide an extra layer of categorization if you need it, including sound source setting overrides, effect chains, and submix sends. Sound classes can be organized in a hierarchy, with the rightmost child classes inheriting values from their parents. They also provide legacy functionality to control effects and mixing, although we recommend using the new features. Audio volume actors placed on your level can control submix and bus sends and enable or disable effects for a specific zone. Finally, you can explicitly assign an actively playing audio component to send to a submix or bus through Blueprint or C++ code. Submixes also support their own effect chains, and they include a different set of effects compared to sound sources. Submix effect chains can be modified through code or audio volumes, allowing you to add or remove temporary effects over an entire category of sounds during gameplay. One of the most common cases is to change the reverb settings on a submix whenever the player enters an audio gameplay volume. One submix effect we'd like to highlight is convolution reverb. It can easily build a representation of our environment's echo properties by using impulse response data. You can generate an impulse response by right-clicking on a sound wave asset. Any wave asset will do, although you'll get more accurate results by using samples recorded in an environment similar to the one you want to reproduce. There's also many impulse response libraries available online. Here's some examples of impulse response sounds from the Lyra project. And here's how convolution reverb can affect a sound sample. Keep in mind the sound will also need to be affected by spatialization to get the full effect. Some submix properties, such as volume, wet, and dry levels, can be modulated through specialized assets. To use them, you need to enable the audio modulation plugin on your project. Modulation can help you mix your game audio dynamically, similar to how a sound engineer uses a mixing console during a live performance to control audio levels and blend in effects. There are several modulation assets that work together to achieve this. Parameters are the topmost layer. They are the named values that will drive properties such as volume level, minimum and maximum frequency. They also define the rules for those values, such as unit conversions, limits, and mix rules. Modulation parameters define the mixing calculations for any drivers they get, without you needing to do any additional work. Modulation generators can provide the signal data. All generator signals operate in a normalized range of 0 to 1, and it's up to parameters to map them to their final value range. LFO generators are similar to their Metasound counterparts. They provide a repeating signal with a specific shape and frequency. Envelope followers take the level from an audio bus as an input and smooth it out over time to create a softer transition. Think of an envelope follower as the bar display on your sound system's equalizer. The levels raise quickly when a loud sound plays, and then smoothly decay back to 0. You can control the climb and decay times through the attack and release properties. The middle layer of your modulation is made from control buses and parameter patches. A control bus takes one or more generators, mixes them, and maps them to a parameter. Parameter patches provide finer control over the output value and let you define how the value is mapped for each of its control bus inputs. You can choose from a set of templates or provide a custom curve. Finally, control bus mixes act as a manual mixing console and can help you audition and control the level for each of its inputs. You can activate and deactivate control buses and mixes from Blueprint and use a mix asset to scale the value of a specific set of control buses from code. This way, you can build code-driven volume and effect controls. The modulation system can make it easy to control mix levels and effect sidechains with almost no programming. This example lowers the volume of an ambient effect every time a music note plays. You can even tweak the assets while the game is running on Pi. Aside from outputting to your speakers, mixing can provide data to additional hardware through endpoint submixes. This can include gamepad speakers and haptics. You can use sound field submixes to encode the signal in a channel-agnostic sound field format, like ambisonics. You can also record the output of a submix into an external wave file or a new sound wave asset for later use in your game. Submixes can also be used for audio analysis to incorporate sound data into other Unreal systems such as gameplay and visual effects. The Audio Synesthesia plugin can analyze a sound wave asset ahead of time and store pre-digested data that would be too costly to calculate while the application is running. You can read this data from Blueprint or C++ to drive gameplay or visuals. For example, you can have a material property or a moving platform that reacts to the relative loudness of dialogue during a conversation. If you can't pre-process and you need to work with live sound data, you can use envelope followers instead. This can be set in your submixes to provide a sound level value at set intervals, and you can subscribe to an envelope from gameplay code to read these values. The trade-off is that you're limited to the overall amplitude of the sound instead of properties that would require more complex and costlier analysis. Niagara can also incorporate submix data into visual effects. You can define audio spectrum parameters in Niagara to read a submix's amplitude data over a set frequency range. Then you can write custom modules to drive particle behaviors based on the audio spectrum data. If you need to profile your audio CPU and memory usage, Unreal Insights is the go-to tool. You can get lots of visual profiling information by running insights with the default and memory flags. Finally, here's some of the most useful console commands for audio debugging and diagnostics. The AU debug command set can help you determine which sound assets, including waves, sources, submixes, and modulators, are currently contributing to the audio output. The AU 3D Visualize command set provides visual feedback on active sound sources and listeners as an overlay to your gameplay. You can enable and disable many sound processing and mixing features through the AU Enable and AU Disable commands. These include most source effects, reverb, and filtering techniques. You can also dump a full memory report with the AU Debug Audio Mem Report command. It will output to a log file that you can open in a text editor and can help you track overall resource usage. This concludes the overview of the audio system. Thanks for watching, and feel free to reach out if you have any questions.